Hello, I am Ronak Pamnani. Me and my team from Group 24 have made a project MandiLens, which is basically a Google Lens for IIT Mandi North Campus. Our problem statement was Know Your Habitat to develop a web or Android platform which performs reverse image search and tells the objects present in the image. In our case, the objects are the buildings of IIT Mandi. So for the data collection, me and my team started taking photos of North Campus buildings from various angles, and we ended up with a data set that includes 8 classes, where each class resembles a building. So we used a VGG19 neural network, which is a pre-trained convolutional neural network of 19 layers, and we changed it to our convenience so that it can detect our images, and we trained it for the end user. We have made a provision so that he can directly upload his image to the Google Colab, and the Google Colab will run our model on that image and give his output that what building is in his image. Thank you. Now Honey will continue explaining VGG19 neural networks.
My roll number is B21165. So what is VGG19, which we used as our pre-built model in our project? First of all, VGG stands for Visual Geometry Group. VGG19 is an innovative object recognition model that supports up to 19 layers. It is trained on ImageNet data and has an accuracy of 92.7%. The network has an image input size of 224 by 224, and its pre-trained network can classify images into 1000 object categories such as keyboard, mouse, pencil, and many animals. As a result, the network has learned rich feature presentation for a wide range of images. VGG19 is a fully connected network with 19 different convolution layers with ReLU as its activation function in, in its hidden layers, and softmax adds its activation function in the output layer. It utilizes the architectural style of zero center normalization on images, convolution, ReLU, max pooling, etc. Now, what do you mean by zero center normalization and convolution? Zero center normalization is used to normalize and reduce dimension in terms of when we perform convolutions later on. The reason this is important is to bring everything down in line in a normalized, streamlined, and orderly fashion. See, basically, convolution is a mathematical way of combining two signals to form a third signal. Here, in the domain of image processing, we add each element of image to its local neighbors weighted by the kernel. Now, there is something called as max pooling after each convolution layer. In short, max pooling is used to reduce the size of the image so that later we need to learn less number of parameters in our model, and hence the model can work faster. Talking about the activation function, first is ReLU. The ReLU function is non-linear activation function that has gained popularity in deep learning domain. ReLU stands for rectified linear unit. The main advantage of using the ReLU function that the neurons will only be deactivated if the output of the linear transformation is less than 0. Then about softmax, it is the activation function in the output. The softmax function can be used for multi-class classification problems. This function returns the probability of a data point belonging to each individual class. The layers used here is VGG is a fully connected layer. But what is fully connected layer? A fully connected layer refers to a neural network in which each neuron applies a linear transformation to the input vector through a weights matrix. So finally, in the output we get the probabilities of the input in which it belongs to various classes, and seeing that we can tell the class of the image. I'll hand it over to Bhuvan.
Yeah, hi, I'm Bhuvan Narula, roll number B21089, and I'll be explaining the GitHub, the Google Colab notebook along with the GitHub repository. So the dataset which we have created on our own, we have uploaded it on a Google Drive. So we'll be directly using the dataset. So we are mounting the Google Drive, and then we are setting path variables to the training and testing dataset, and we are setting the batch size as 16 for our model training. So we are splitting the training dataset into the training and validation dataset, and we are specifying the validation split to be of 0.3, and we need to specify a common seed for both so that both split can be independent of each other. and we are resizing the images to be of the resolution 299 by 299. Initially these images are in the order of 3000 by 3000. We don't require such detailed images, so we are downsizing it to 299 by 299. We are using a total of 300 images, approximately 300, out of it 208 we are using for training and remaining 89 we are using for validation. And since our data set is small, we will be using transfer learning. In transfer learning we are using a VGG19 model. This model contains 19 layers and has been pre-trained on the ImageNet dataset. ImageNet dataset contains anything from buildings to airplanes to many other things. So we'll be using the pre-trained model, on which on the output side we'll be implementing our own custom layers. So so we create a VGG19 model in which we specify the image shape which it will get as an input, and we specify the weights to be that of the ImageNet dataset when it was trained on the ImageNet dataset, and we mention that include or false, meaning that at the output side we'll be implementing our own custom layers. We don't require those. So after that, for the remaining layers we specify them to be non-trainable, because we have already set the weights. We don't want these weights to change, so we set them as non-trainable. And on the output side we first add a layer of flatten, because these the input which we'll get from the feature extraction side will be of 2D, will be of 3D format due to CNN. So so first we need to flatten it out to be a 1D array, and after to flatten it out we simply add an output layer which is a dense layer of 8 neurons, since 8 is the number of classes we are using. And the activation function is softmax, because we will be predicting the category. So we create a model which with input as the VGG19 and output as these two layers which we have created. Now seeing the summary of this model, so these layers are part of the VGG19 pre-built model, and at the end we have added two custom layers, flatten and dense. And as we can see, there are total of 20 million parameters, and we are just training 331,000 out of it. The remaining are already pre-trained. We won't be changing them. So now that our model is trained, we train it in 10 epochs. I won't be training right now. We have already pre-trained the model and saved the model. We'll just be loading the same model. And on training, as we can see, as we are training a lot less parameters, the training is quite fast, and we get a maximum accuracy of 94% on the validation. On training it was pretty good fit. We can't say that it is overfit, because it is already pre-trained on ImageNet dataset. It has already seen a lot of buildings, so this is a good thing. And as the validation accuracy is not dropping, we'll accept this result. And after that we are importing the testing dataset which we'll be using for testing. It contains 34 images which are independent of the training and validation dataset. So first I'll be importing the pre-trained model. The pre-trained model has been saved and on the GitHub repository. We download that model and we'll just load that model directly to Keras. After loading the model, we can proceed with our evaluation of the model. So if we evaluate the results of the model, first we get a list of the labels, since on the prediction side, not on this evaluation, when we will be needing to predict the label of the image, we'll as Keras stores the label in one hot encoding, it doesn't store the labels. So we create a list of the labels which are available to us, and as from the evaluation we can see we get an accuracy of 97.06%, which is very nice accuracy. So if we want to save this dataset, as we want to save this model, we can save the model using this, and since we have already saved this model, we don't need to save it again. And now that we are predicting on a sample prediction, we take any two images random. We will be using oak image, and so if we take this image and if I show you this image, it is same as this image. This is an oak mesh, image of an oak mesh. And now if I predict on this image, as you can see, this is an image of an oak mesh, and now if I predict on this image, we get the prediction of the oak, which is correct. So the model is working correctly. So now if the user wants to implement its own, if the user wants to predict the label or the class of his own image, so we use the function files.upload, which is function made available in Collab, through which the user can upload its own custom file. So here I'll upload a custom image which I have downloaded. Like this, the image will upload. The image is same as this. If this will take a bit of a time. So the image is same as this. It is the image of a flower. We have added a flower just to have a variety in our model training. So when we predict on this flower, we get the prediction as flower 1, which is true. This is actually marigold flower, but we just use the label as flower 1 as we aren't using any other flower. So yeah, the model works correctly. And yeah, now on to the GitHub. In GitHub we have mentioned the installation procedure. Like if the user wants to custom train on our data set, there is a link to Google Drive, and the user will need to create the shortcut of this folder in his own drive. The user will be mounting his own Google Drive here in Google Colab. So he needs to do this, and after that the pretty much the explanation is made available in the collab itself. And we are using 8 classes: A9, A10, A13, A16, A17, oak, trago, and any flower which is marigold flower. So we are using these 8 classes, and the working is as mentioned. We are using the transfer learning with VGG19 model. We get an accuracy of 94% on validation and 97% on testing, which is very nice. And in future we plan to implement a YOLO based model for the same, like in which the user can directly give a live camera feed, maybe through an Android app, and on that live camera feed we can create bounding boxes which show which building is what is the name of any building.
Hello everyone, this is Chinmayee B21123. Now let me tell you about convolutional neural networks. These are used for classification and computer vision tasks. There are mainly 3 types of layers, like convolutional layer, pooling layer, and fully connected layer. Convolutional layer, it requires a few components which are the input data, a filter, and feature map. These are actually core building blocks of CNN. An input can be a color image or a black and white image. If it is a color image, there will be 3 layers, each layer for primary colors like RGB. This is known as convolution. We can detect features by calculating dot product of filters with the input matrix. Each output value in the feature map does not have to be connected to each pixel value in the input image. It only needs to connect to the respective field where the filter is being applied. And weights in the feature detect and the weights in the feature detector remains fixed as it moves across the image, which is also known as parameter sharing. The weight values can be adjusted during training through the process of backpropagation and gradient descent. However, there are 3 hypermeters which affect the volume size of the input that needs to be set before the training of the neural network begins. These include the number of filters, stride, and zero padding. The number of filters affects the depth of the output, and stride is the distance or the number of pixels that filter moves over the input matrix. And zero padding is usually done when the filter do not fit the input image, which sets all the elements that fall outside of the input matrix to 0, producing a larger or equally sized input. There are 3 types of padding, like valid padding, same padding, and full padding.
Greetings to all the respective faculty members out there. This is Mourya Kondawar, and my roll number is B21016. I will be taking over on the pooling layers and fully connected layers from here on. The pooling operation involves the sliding of a 2-dimensional filter over each channel of feature map and summarizing the features lying within the region covered by the filter. For a feature map having dimensions nh by nw by nc, the dimensions of output obtained after a pooling layer is denoted by nh minus f plus 1 whole divided by s into nw minus f plus 1 by s into nc, where nh is the height of the feature map, nw is the width of the feature map, nc is the number of channels in the feature map, f is the size of filter, and s is the stride length. Let's move on to why are we supposed to use pooling layers. Pooling layers are used to reduce the dimensions of the feature maps. Thus, it reduces the number of parameters to learn and the amount of computation performed in the network. The pooling layer summarizes the features present in a region of the feature map and of the feature map generated by a convolution layer. So, further operations are performed on. Sorry about that. So further operations are performed on summarized features instead of precisely positioned features generated by the convolution layer. This makes the model more robust to variations in the position of the features in the input image. Let's move on to the next slide. In the slide, in the above console, we can see that the input layer has a dimension of 300 by 300 first. And as we start convoluting and extracting the features, and as we use our first pooling layer, our dimension reduces to 149 by 149. Similarly, we can see that there are a total of 5 pooling layers and 16 convoluting layers that use finally make our input with of a dimension 9 by 9. We repeat the convolution many times in order to extract an appropriate number of features, which will help in differentiating and classifying our input. Let's move on to fully connected layer. The pixel values of the input image are not directly connected to the output layer in partially connected layers. However, in the fully connected layer, each node in the output layer connects directly to a node in the previous layer. This layer performs the task of classification based on the features extracted through the previous layers and their different filters. While convolution and pooling layers tend to use ReLU functions, fully connected layers usually leverage a softmax activation function to classify inputs appropriately, producing a probability from 0 to 1. Thank you.
So, hi guys, hi everyone out there. My name is Mantavya Gupta and my roll number is B21015. My fellow teammates have already explained like what was the question, how did we approach the question, what was the data sets, what is CNN and everything. So, at last, I would conclude this video by telling how important CNN is in a practical life. So, before starting, let me tell you what is computer vision and what is the agenda of computer vision. See, the agenda of computer vision, it is a field with an agenda that enable so that we can train our computers to see the world as we humans do, and this agenda is achieved with the help of deep learning, and that too particularly CNN, convolutional neural networks. So here thereby I present few important applications of CNN. The first is facial recognition and biometric authentication. See, CNN has a very great ability to classify unique to extract unique features, due to which it has a very good capability to recognize faces irrespective of where the face is in the photo, or what is the shadow or the pose in of the face in the photo. This photo there then this photo and this face can be used also, it can be also used in biometric authentications for various logs and everything. The second very important use comes in the field of medicine, that to biomedical imaging, in which we train a model with the x-rays and MRIs of the pre-existing patients, and thereby we try to guess, or try to find the fractures or tumors in the upcoming new patients just by looking the x-ray and MRIs and everything. The third application comes in autonomous driving. See, CNN has a very good capability to extract features, so it can recognize obstacles, turns and everything, and road signs, etc. As a result, CNN plays a very important role in the primary algorithms uh, of self-driving cars. So hereby I conclude our video, and thank you everybody for hearing us out.